There we go. Seems to be working now. Hi, welcome back to Chem 140. We're going to finish Unit 11 today, just so we can stay with the syllabus. I actually think that with the schedule that we are going at, we're going to run out of content before we run out of time, so we're going to have a bunch of review sessions at the end before the final, which is nice. Give students a chance to take a breather and catch up and that sort of thing. So, what do we have on the agenda? So, there is a lab worksheet that is due today, and it closes tomorrow. So once the due date passes, remember you have 24 hours to turn it in before it closes for good. Make sure you get that in by the deadline. And then quiz number 5, which is units 9 and 10, is due on Monday the 8th. And what else? Oh, there's one more agenda item we'll just draw over here. So tomorrow, oops, is my cake day. Woo. There's my birthday cake that I'm drawing. I'm going to go out and buy myself a birthday cake. That actually looks more like a fedora with candles coming out of it, but you know. But yeah, happy birthday, me. That's tomorrow. We're going to continue doing our naming nomenclature rules. I hear Maya meowing. There's Maya. Maya, come say hi to everybody. They miss you. Come on up. Come on up. Say hi. Say hi. Maya. Don't just jump on my lap. Say hi. Say hi. Say hi. Say hi. Say hi. I mean, hopefully you heard her. She really wanted to say hi. Alright. We're going to continue naming stuff. So we did ionic compounds all day yesterday, and ionic compounds are probably the longest section because it's just getting used to, like, doing nomenclature. We're going to do molecular compounds and acids today. Molecular compounds follow a different pattern, and you can see that the wording in my boxes at the top here is slightly different. And that there are these pound symbols here, or I guess we would call them hashtags nowadays. So we have these hashtags, and these are actual number symbols. So in the boxes with the hashtags, you're going to apply something that describes the number of that element and append it to its name. Now, it's attached to the name, as you can see, because you're going to put it as a prefix. And so the way that that's going to work is first we're going to name that first element, and then we're going to name the second element with "ide." Now, because molecular compounds only have non-metals in them, you know all the ides already because we did all of that yesterday when naming the anions, right? So you're going to name the first element as if it were a metal. It won't be, but that's okay. And then you're going to name the second element and stick "ide" on the end. Now I just keep hearing her out of the corner of my ears. Oh, it's because she's back. Yes, I'm teaching. You literally were just here. She left the room for like 2 seconds and came back. Did you have something else to say? Did you? Hello? Hello? Yeah, maybe. Whatever. Cats, ladies and gentlemen. Maya, I don't remember where I was now. You distracted me. We're going to name the first element as if it was a metal, but again, it's a non-metal. We're going to name the second element with "ide." Now, there is a property that is used to describe which element goes first and which element goes second, and that's called electronegativity. And we're going to describe electronegativity more in 161. So for now, it's going to seem kind of weird, like, which element goes first? Which one goes second? And so we're going to just summarize that as the more positive element goes first, and I'm going to tell you which element that is by writing out the formula. So for example, if I had carbons and oxygens in a formula, I would write it like this. The carbon goes first because the carbon is more positive than the oxygen. Now, a good rubric for what's more positive is just simply which one's further to the left, or which one's further down. However, that doesn't always work, and we'll show a numerical value table, excuse me, of all of that information next quarter. So don't worry about it for now. Now, in the boxes with the number symbol, we're going to use a numeric prefix. You may have seen these prefixes before. Here they are. Mono, di, tri, tetra, penta, etc. Depending on how many of that element you have, you're going to apply that prefix to the front in the space where the number symbol is. So, for example, if I had 3 nitrogens, so something like this, for this first term, I would go tri, because there were 3 of them, nitrogen. And there would not be a space here. I just screwed up when I wrote that. So let me fix that. I don't know why I rewrote nitrogen. I could have just rewritten tri. There you go. So you do something like that. Now, very, very important, you only use numeric prefixes for covalent compounds. So no numeric prefixes on anything we did yesterday, okay? Likewise, no Roman numerals on anything we're doing today. So today, no Roman numerals, okay? There are no Roman numerals on anything other than the charge on a positively charged ion. And there are no ions in molecular compounds, right? All right. Now, we do have a handful of exceptions for writing these numeric prefixes that are in the interest of like spelling and simplicity. So the first exception is that if there's only one element or one atom of the first element, then you don't write mono. So for example, for CO2, we don't write monocarbon dioxide. We just say carbon dioxide. Likewise with CO, we would say carbon, because there's only one of the first one. We just write the element name. And then there is one of the second one, so we would do monoxide. There you go. Now, you might have noticed, wait a second, Wes. This is you speaking. This is what you sound like. I assume. I don't know any of your voices. But, wait a second, there's an O on the end, and oxygen also begins with O. What do I do? And the answer is, if you get a situation where your prefix bumps into an O, then it sounds kind of stupid. And so what we do is we get rid of the O on the prefix. My cord is in the way, so I'm having trouble drawing there. So instead of having something like this, monoxide, which then sounds like it's French, I don't know. We get rid of the O on the prefix, and then just slide them together. So that would be one word, monoxide. So the vowel combinations that we have decided sound dumb are AO and OO. So you'll notice that for these you end in I, and these are okay. But for everything else, we would just get rid of the last letter here for oxide, just to make it sound better. Now this is just something that we do. Now be mindful of that rule when... Oh, I forgot to scribble out the one for mono. Be mindful of that rule when you are typing your answers into Canvas, because Canvas is going to be very picky about your spelling. And so I'm going to put a warning on the naming page, is that be careful with spelling, make sure you don't misspell anything. Because if you make any typos, it may mark it incorrect. I've tried to set a setting on most compounds. Not all of them, because Canvas's functionality is limited. I think it's called Levenshtein distance. And basically what that means is that how many changes or permutations to what is typed can you make? And I've set it to 2. And so what that basically means is that if this was the word I expected you to write, then a Levenshtein distance of 1 would be, oh, I forgot a letter. So in step 1, I deleted the letter U. And then in step 2, oops, I don't know why I'm writing the circle before. I added the U in. So in other words, you can basically superimpose, or not superimpose, right, transpose 2 letters most of the time. So if you don't put in the letter or something, then it's usually okay. So Canvas should accept this, obviously, because it's the right answer. But it would also accept either of these, because you're within a Levenstein distance of 2. In terms of, you can add or delete up to 2 characters to get what you were supposed to. Incidentally, what this also means is that you could type in something like this and put it like a capital Q at the end, and it should accept it as correct. Although I would not test this, so just be mindful of that. Don't start adding Q's to the end of all of your answers just to see if the Levenstein distance thing is working. Because some of them I can't do that for, because Canvas cannot account for some of the errors. The takeaway is that you have a little bit of flexibility, but still be as careful as you can. And then, like we said on the previous slide, never use Roman numerals in anything molecular / covalent. All right, so those are the rules. Let me just give you some compounds. I'm going to have you try these because these are typically pretty easy. You don't really need me to do an example. So type what you think the answer is for this in the chat. Remember that the first element is normal. Its name as you would see it on the periodic table. And the second element gets I'd. And then apply your number prefixes. So type your answer in the chat to what you think this is, N2O5. We'll go over it in just a second. So you got the number of, or I'm sorry, so you got the elements, but don't forget the number prefixes. So how would you adjust your name there? It might seem weird, but it's actually the right name. So let's go over the answer here. So this is nitrogen. This is oxide. And then we're going to do a number prefix for each. So 2 is di, and then 5 is penta. We'll just get rid of the A on the end because we get an AO combination. So there you go. Oh, I think you had home keys issue there. Your hand is one set of letters too far to the right. Domophogen pentoxide is definitely not the name. All right, try this one. Remember what happens when you have one of the first element. Type your answer in the chat, and we'll go over it in a second. There you go, very good. So, this one's sulfur. Oops. Oh, what's happening? Why is my pen doing that? Let's try that again here. This one's oxygen, which again we'll do oxide. And there's two of them, so I do that. We don't write mono for the first thing. Alright, what do you call this? I'll give you a hint, it's not water. Can't call it water. I mean, you could call it water, but applying the rules that we have described here, what would you write for H2O? There you go, very good. So, we've got two hydrogens, so there's our dihydrogen, and then we've got one oxygen, so that's oxide. But we do include mono for the second element, so dihydrogen monoxide. Now, water, or dihydrogen monoxide, is the one substance that begins with an H that we don't use the acid rules for. Mostly because water is, by definition, the weakest possible acid. If you are a weaker acid than water, you're called a base. Not that you would know that, because we haven't done any acid-base chemistry, and we won't until 163. But that's just a little extra information for you. Now, an interesting thing about being named dihydrogen monoxide is it makes it sound scary, right? Now, it is possible to use that information that, ooh, it sounds chemically, chemicals, and take advantage of people who don't know better, which is where this comes from. As an example, I'm going to show you the petition to ban dihydrogen monoxide. This is a joke that was pulled in. I mean, everybody has done this. I'm pretty sure at some point, but a long time ago, I think the earliest two instances I can think of trying to do this joke to raise chemistry and chemical nomenclature awareness. I'm going to give you two examples. One was a Senate hearing, I believe, something like that, where the petition was passed by the Senate to ban dihydrogen monoxide. And they made all of these arguments that you're going to see here. They eventually voted to ban it. And then afterward, they said, hey, guess what? You banned water. And everyone went, ha, 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 that's funny. And it was a whole, really just to like highlight the fact that people weren't aware of chemistry. The second instance of this happened at a radio station where on April Fools, they said, hey, have you heard about this new chemical dihydrogen monoxide? Yeah, it's in everything. It's even in your drinking water. Mass panic. The radio station was shut down within the hour because so many people called in. Hysteria. Like, oh my god, what the fuck is this, basically? Now, here's the quiz for you. One of those stories I told you took place in Australia. The other one took place in Atlanta, Georgia. Which one was which? I'll let you think about that while we talk about some of the bad things, quote unquote, that dihydrogen monoxide can do. And so here they are. So there are many names for dihydrogen monoxide. One of those is hydroxyl acid, and it is the substance that is the major component of acid rain. How terrible. Now, dihydrogen monoxide does contribute to the greenhouse effect. In fact, it is more of a contributor than carbon dioxide. And carbon dioxide is the one that we're worried about, believe it or not. If you are exposed to it, it can cause severe burns. And if you breathe it, you will die. That's how deadly this stuff is. Now, it also causes erosion of our landscape. It wears it right away. Like, Grand Canyon, just completely torn to pieces by this stuff. And also, it accelerates corrosion and rusting. Like, all the rust that you might have seen anywhere, it's because of this. Now, if you use a vehicle of some sort, it screws with your brakes, it makes them less effective, and it can get into electrical circuits and cause them to short out. And it's just so bad. Every single person who has died of cancer has this in their body. Holy shit, dude. Like, that's awful. And despite how bad this substance is, DHMO is used in the following places. It's used in industry as a solvent and coolant. It's used in nuclear power. So scary. It's used to make styrofoam. It's used as a fire retardant. It's used as cruel animal research. It's used to distribute pesticides. Even if you wash your produce, you can't get rid of it. It's still there. It's in your junk food. It's in other food. And it's fucking water. Oops, I misspelled water. Hold on. I got a little carried away. It's water! So, obviously that was all a joke. Because it's freaking water, right? Of course water will kill you if you breathe it in. That's called drowning. Of course it can cause severe burns. Boiling water is really freaking hot, right? Every person has it if they die of cancer because water is in your body. You need water to live. Like, so you can see how we have twisted the facts by using this chemically sounding name. And they, on the radio station, which obviously was in America because Americans don't know fuck about science, is that, I say that as a Canadian. Sorry. I'm half American, but this is my Canadian superiority because my mother's from Quebec, I guess. I don't know. At the radio station example, they listed all of these things and people panicked. They called in and they were like, holy crap, I can't believe that this is in our water and this is the first I'm hearing of it? I want this out of here. I'm not touching your water. And so the radio station was shut down in an hour. During the break, I'll go find the article for you. I think it was Atlanta. It was definitely Georgia or Florida. It was somewhere over there. But yeah, this sort of thing is something that anti-science people want to pull on you all the time. And so, for example, with the vaccine, one of the common scares is that they list all of the chemicals in the vaccine, and they're like, do you want mercury in you? And like, no, of course you don't want mercury, but conjugated mercury as a stabilizer for this specific purpose in the vaccine is totally fine. And the only way to know that is to actually do the research on like Wikipedia or read scientific articles or ask a biology instructor, for example, and get that information rather than just believing, oh my god, it's mercury! Ah! Oh my god, it's dihydrogen monoxide! Ah! Another example of people using language that other people don't know and understand. A long time ago, there was a show called The Man Show. It was this really stupid sketch comedy thing. But one of the sketches that I thought was the funniest, and it really highlights this point, is that they went out with a clipboard and asked people to sign to end women's suffrage. And if you don't know what suffrage is, that's a problem. Suffrage is the right to vote, but it sounds like something else. And so I remember just seeing women signing away their rights to vote and that of all women, saying, I don't want women to suffer. Like, no, that's not what that means. Don't just believe what things mean by reading the word, because this right here sounds a lot scarier than it actually is. In fact, if you're taking a sip, if you're drinking something, you're drinking it right now. Dihydrogen monoxide. All right, so on the screen here, that's my nomenclature sketch, or whatever you want to call it. And obviously, like, if you take any... Oh, hold on, my phone is buzzing at me. If you take anything out of this class, like, not just today's lecture, but in general, and that is, like, a critique or sort of, like, skepticism of, like, when people throw chemically sounding names at you and you aren't immediately terrified or scared of them, then I think that this class has been successful. So, don't be terrified by names that look like this. Try and figure out what they actually mean based on the nomenclature rules. All right, so go ahead and name these compounds. I have some formulas at the top here. Down at the bottom, what I want you to do is I want you to take the names and turn them into formulas. Turns out that's actually really easy to do, because you can see the number prefix and you can also see the element. So go ahead and do that and write the formula for those. Type everything in the chat, and we'll come back in about 5 minutes, and then we'll go name acids, and we'll be done with nomenclature. So see you in a bit. All right, one more minute. We'll go over the answers. All right, so here we go. So when I do these, I just do one element and its number at a time. So this would be dinitrogen. And then I have one oxygen, so I'd go monoxide. And then Cl2 would be dichlorine. Be careful. Oh, uh-oh. What's going on? Apparently my pen has functionality in it that it's not supposed to, because I thought I turned that off. That might have been what's been doing that. So dichlorine. Make sure you do dichlorine and not dichloride, because ide is only for the second element. Oops, hold on. I didn't actually do the number for that one. So there's 3 oxygens, so this would be trioxide. We got sulfur. And then there's 6 fluorine, so hexafluoride. You might look at that and be like, wait a second, how the heck do you connect 6 things to something? Wouldn't that break the octet rule? Totally does. We're going to learn about that in 161. That the octet rule is not actually a limit for some elements. Elements like to conform to it, but you can actually go past it. All of the elements and formulas that we do in this class, though, in terms of drawing a Lewis structure, will not exceed the octet rule. Just the formulas. I might show you, like this one. Like, what the hell is going on here, right? Well, whatever is going on here, we can still name it. So, tetraphos for us. And then there's 10 oxygens, so that would be deca, but you don't actually have the AO combo there. So, decoxide. There you go. All right, very good. Now I'll do the same thing but backwards. So di is 2. Boron is this, so I would write that. Tri is 3. Oxide is O. There you go. We got carbon. Boop. There you go. Disulfide would be S2. We got oxygen. Difluoride would be F2. There you go. That's all there is to it. The hardest part about naming covalent or molecular compounds is that it's easy to mix up the rules when you see covalent compounds mixed together with ionic compounds. So just be aware of that. Make sure that your first question that you are asking when you look at any problem is this ionic or molecular or acid? And that you put it in the right category and then you apply the correct rule. If you do that, you can't go wrong. All right, let's do the acids. Acids are special nomenclature algorithms that require you to look at the polyatomic ion or the anion that is present and then put it in a category from there. So first let's define what an acid is. An acid has this in it, H+. So if you split your compound together, or if you split your compound apart, I should say, part of it will be H+, and the rest will be the anion. So you can kind of think of acids as being between, so if I have ionic and covalent, in the midpoint somewhere is where acids live. So you can have stuff that is sort of ionic and sort of covalent, and acids are one of those substances. So acids, despite only having nonmetals, will still dissociate into ions. However, one of those ions always will be H+. Okay? And so we list the H first to show that. So for example, in HCl, all the H's become H+. Everything else that's attached must be oppositely charged to balance out the total charge at 0. So that's why we have H+ and Cl-. Down here we have H3PO4. Well, if I have 3 H+ on here, what must be the charge of this thing? It must be the opposite charge to balance it out. Now, you're going to want to do this process and split your acid into its ions, because what we'll do is we're going to look at the ion that you produce that separates apart from its H's, and we're going to look at its name. So, for example, this is chloride. This is phosphate. And you'll notice that I'm underlining the ending there. The ending dictates how you name the acid. So you need to know what ions go into the acid and what their names are. Once you know that information, you can then give it the correct name. Now, in some cases, the state even matters. We'll talk about that in just a second here. But the first set of acids that we're going to name, right here, for set of rules number 1, is the binary acid. Now, the binary acid rules actually encompass everything that includes anything that ends with "ide." So, for example, here we've got fluoride, chloride, sulfide, etc. For anything using the "ide" rule, the state of the acid matters. If I don't give you a state, assume aqueous. But if I do give you a state, then you have to use the correct algorithm. So the first algorithm is, if the state is gaseous, this is what you do. You write the word hydrogen, and then you name the anion with "ide", so whatever it is. So for example, something like this would be hydrogen fluoride, but only if it's in the gas state. So in other words, you're basically naming this like a covalent compound if it's in the gas state. Now, if it's not in the gas state and is instead aqueous, you use this rule instead. You write hydro something ic acid. So in this blank, you're going to take the name of the ion with "ide" removed. So for example, for fluoride right here, if I had HF as an aqueous, I would call this hydro something ic acid. And in the blank, I would get rid of "ide." So I'd go fluoric acid. There you go. So HF as an aqueous acid is hydrofluoric acid. Now, there are some instances where you remove the "ide and the anion sounds dumb or too short or something like that. So with sulfur and phosphorus, here's what they sound like as anions. But if we turn these into stems and we get rid of the "ide", then we start getting into naming conflicts because there are a bunch of things that have sulfur in it. So what we have to do is make this the stem. And you'll see this on the next slide in just a second. So H2S, for example, as an acid in the aqueous state would be hydrosulfuric acid, as opposed to hydrosulfic acid, which I guess might be something different. I don't know. And then H3P would be hydrophosphoric acid, assuming that that exists. I've never heard of H3P. I've heard of PH3, which is base, though. All right. Now, you'll notice that up here I did this inclusion. That's because the cyanide anion also follows this algorithm, and its name is hydrocyanic acid. So just keep that in mind. If you see HCN on your exam, make sure that you name it using these rules. All right, so we already did the fluorine ones, and you could probably easily do the bromine ones. So I'm just going to put those answers on there. That was naming rules number 1. So anything that ends with "ide" follows these rules. What if it ends in something different? If your ion ends in 8, for example, when we had this earlier, this ends in 8. What's the naming rule for that? Well, you get rid of 8, and then you add ic acid. So for instance, if I had this, first I would split it into its pieces and say, oh, this is nitrate. It ends in 8, so it follows this rule. So this must be called, therefore, we'll get rid of the 8 and add ic acid, or nitric acid. Now, if your polyatomic ion ends in "ite," it's the same process, except instead of ic acid, you put us acid at the end. So you'll notice that the difference here is subtle, and it is easy to get these mixed up. So just be careful. So those are all the acid rules, and it's basically just, what's the ending? Which rule do I use? Now, the hardest part about this is trying to remember what the polyatomic ions are, because if I look at this and I say, oh, what the hell is this called? And I don't know what this is right off the top of my head, then I gotta go do research, right? And that's no good. I would not trust Google for looking up acid names, because you're gonna get a bunch of common names, and if you type those into your Canvas worksheet, it will, or your quiz or whatever, obviously it will be marked wrong, and then I'll know, oh, so you're Googling your answers, huh? And not actually looking them up in the textbook, for instance. Make sure you're referring to good sources, is what I'm saying. Don't just Google everything and take the first answer. So in Unit 6, if you look up this ion, you would find that it is, I lost my stylus, there we go. This is called acetate. It ends in 8, so we're going to get rid of the 8 and put ic acid. And so the name for this would be acetic acid. And you've probably heard of acetic acid before. This is actually vinegar. All right, how about this one? HNO2. What I want you to do is try and name that one for me. Type its name in the chat once you got it. Make sure you look up the polyatomic ion, and then apply the correct rule. All right, let's go over the answer here. So this ion NO2 with a minus charge, because this would be H+. This is nitrite. Ends in ite. So HNO2 must be nitrous acid. So nitric acid would be HNO3. Nitrous acid would be HNO2. All right. We already talked about how we changed the stems for sulfur and phosphorus. So these are the stems. So go ahead and name these two things using the correct nomenclature. Oops. I set the pen down and so it... Oh, pfft. There we go. So I want you to tell me what the name of H2SO3 is and what H3PO4 is. Again, you have to look at the polyatomic ions. What is the name of this thing? What is the name of this thing? Tear the end off of it and attach it to the correct algorithm. All right, let's go over the answer. So if we split this into its pieces, there's my H pluses. SO3 must be 2 minus to balance that out. And this is sulfite. So it ends in ite, so we would end it in us. So this would be sulfurous acid. And then for the other one here, we've got all my H pluses. This must be PO4 with a 3 minus charge. And this is phosphate. I ran out of space, sorry. And so that would make this, we get rid of the 8 and we would put phosphoric acid. There you go. So definitely on the right track. You just got to know your polyatomic ions. All right. So here's some more practice with that. So I want you to take your list of polyatomic ions and comb over it trying to find these ions. And then use the nomenclature rules to name them correctly. Down at the bottom, I have the names already written. You're going to have to translate them back into acids. That's a lot more tricky than it sounds. So remember that we're adding some ending and then acid to it. So, for example, sulfuric acid, you'd have to get rid of the ic acid. What does ic mean? Oh, it was this formula, so on and so forth. It was sulfate, for example. Okay? All right, go ahead and try that. We'll go over the answers in about 5 or 6 minutes, and then we'll take a break, and I'll see if we can collect any questions for the Q&A. All right, see you in a bit. 1 or 2 more minutes, and then we'll go over the answers. Oh, I just looked at the clock, actually. So what we'll do here is, if people are still working on these, you can go ahead and keep doing that during the break. I'm going to put the break timer up here, because I don't want to take the break at, like, 4. So let me, oops, hold on. I had changed the layout for something I was doing yesterday. I'm going to start the timer. You can keep working on those and type your answers in the chat if you want. But what I'd also like you to do is, if you had questions that you wanted to go over for, like, the review session at the end of the period today, go ahead and type those in the chat too, and we'll get to those after. So I'll do that, and we'll see you in 10 minutes. Alright, we're back. Apparently my playlist shuffler, like, I've been hitting shuffle on this, and it's playing, like, the first 4 songs over and over and over again, despite there being 15 of them in this playlist, so... Oh well. That's how randomness works. So let's go over the answers here. And then we'll answer that lab question, and then I guess we'll call it a day, because that was the only question I got. So... Alright, so we need to know what these polyatomic ions are in order to name these. So first, we're going to split off all of our H pluses. So each of these has H pluses in there. So this will have 2 of them. And so on and so forth. And whatever's left is going to be our ion, like we said before. And then we just need to go look up its name. So what is this? This is perchlorate. And so if I'm going to name it, I would get rid of the 8, and it would become perchloric acid, because 8 becomes ic acid. Same thing down here for BRO minus. This is hypobromite. We would get rid of the ite, and this would become hypobromous acid. There you go. So really, naming acids is just an exercise in identifying the polyatomic ion, writing out its name, and then modifying it based on the rule that we used. So there you go. Dichromate becomes dichromic acid. Remember that cyanide is the weird one? Because it ends in ide, it follows the ide rule. And then for this last one here, this is phosphite, which means that it becomes phosphorus acid. Do note that there is this O here is not present in the element name. So phosphorus, the element, doesn't have that O in there. But phosphorus, which is the name of an acid, does have that O. So that's a typo that I think I made for years. I had been misspelling phosphorus forever because I had just been including that O in it all the time. So you do want that O in the acid. You do not want it in the element name by itself. So just P by itself is this. Notice that there's no O there. All right, so now we take these names and work backwards. And so the way that we do that, or at least the way that I do that, is I get rid of the prefix and see what I have. So I have ic was used to replace 8. So this is actually sulfate. And so then I go look up what that is, and that's this. And so I have a 2 minus. I need 2 H's to fix that to make it neutral. There's my formula. That's my thought process for this. So again, ic acid is used to replace 8, so this would be nitrate. I then go look up what that is. I then write its formula. So another ic acid, so this is chrome 8. I go look that up. That's what it looks like. There's the formula. Down here I have us acid. That means that that's an ite, so this is hypochlorite, which is this. And so the formula must be HClO. And same thing down here, so this is periodate. Don't get conned into thinking that it's periodic acid. It's periodic acid. And there you go. All right, I think that that's everything for nomenclature. So let me know if you have any questions on how we did that. Really, the only way to get around, or the only way to get to mastering nomenclature is you got to practice, 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 practice. So there are a lot of rules, and they're all sort of similar, and it's real easy to make mistakes. So be careful with the rules, and for the first bit, use your notes and just go through the rules every time. Like, okay, what category is this? Is this ionic, molecular, or acid? Okay, use the correct rules, and then name it. And then eventually you stop having to look up your notes every time. So practice, practice, practice. Hooray! All right, so let me go over here real quick. So there was a question about, and we don't actually need this, so I'll just push it off the screen. There was a question about how do you answer questions number 14 and 15 on the lab. And so those questions, I believe, were that and this. And if that's not right, correct me. Let me know. Now, one of these is a lot easier to do than the other one. And so I'm going to sort of leave that to you to look at all of your data and then say, oh, well, this one has this conductivity because it's this type of molecule. But there is a blurb in the documentation that says that conductivity occurs only when charged ions are detected. Now, it says nothing about the identity. So in other words, if I had this and this, they should have the same conductivity because they're the same number of ions. I've got Na plus and Cl minus, or I've got K plus and Br minus. And then remember that these numbers are concentration, which is just how much stuff there is in the bottle. We're going to talk about that concentration in Unit 16 at the very end of the quarter. So your task is going to be, okay, well, what does KOH do? Is it ionic or is it molecular? Go look up in your notes which category that is, and based on what you find, what would you predict its conductivity to be? Use the data that you have collected from the video. Now, I realize that this is a little bit obtuse because you haven't tested any other solutions. We only tested NaCl solutions. But the documentation does tell you this about conductivity. And really what I think the issue comes down to is a lot of people don't read the documentation. So make sure that you are reading the lab PDF very thoroughly, because I don't ask you questions that aren't actually in there, but I will try to obfuscate them and hide them real well, okay? So that's my answer for number 15, or 14 and 15. I can't really say much more because I can't just give away the answer there. But if you're stuck on that, remember that you tested ionic compounds and covalent compounds, and you got results for both. And that the identity doesn't matter, it's just if there's ions or not, right? Alright, no problem. That was the only question I got. So if there aren't any other questions, I'm going to shut the stream down here because, I mean, we're already at 3:55 for a Wednesday stream. So I do want to thank everybody for coming out to the lecture today. Oops, I got to hit a button here. Make sure, I am going to put quiz number 6 online. It'll be due next Wednesday, so a week from today. Make sure that you get lab number 3 in as soon as you can. That will close tomorrow. And then quizzes 5 and 6 will be due next week sometime. So, other than that, have a wonderful weekend. And take it easy. And happy birthday to me. Hee hee.